Hello everyone, my name is Berke and my teammates are Altay and Berkecan. Our project is developing a self-leveling quadcopter. To do so, we have integrated mechanical and electrical components to develop a flight controller alternative to commercial controllers. Our aim is to use our hardware and software together to govern the orientation and flight of the drone. To have the drone flying, numerous subsystems should simultaneously work. Commercial, ready-to-use subsystems can be bought and implemented on the quadcopter, but in our project, we aim to develop our versions of these required systems as much as possible. We have written a calibrator and a data acquisition system for our IMU sensor, implemented a filter on raw data, and developed a PID algorithm. Our quadcopter consists of 4 brushless DC motors, their propellers, and electronic speed controllers. Attitude data is acquired from 6 degree of freedom accelerometer and gyroscope connected to Arduino Uno and transmits quadcopter attitude to Raspberry Pi, where the control system is implemented. The communication between the sensor and Arduino is governed by I2C protocols, and serial communication protocol is used between Arduino and Raspberry Pi. To control the flight, a PlayStation 4 DualShock controller is linked to the Raspberry Pi via Bluetooth. This setup is powered by a lithium polymer battery, which is capable of sustaining 10 minutes of medium performance flight. The battery has 2800 mAh energy charge and 35C C rating. The battery powers all subsystems such as ESCs, Raspberry Pi, brushless DC motors, and Arduino via the power distribution board, which is integrated in the quadcopter frame. We have built a user interface which communicates with Raspberry Pi on the frame in real time via a web server. Through this interface, the user is able to monitor the current attitude of the drone, drive the motors, and see graphs which include the reference state fed by the user through the PS4 controller, PID output, and current read attitude for roll and pitch. 3D model of our drone is converted to STL and then loaded on the web browser to represent real-time orientation.
Accelerometer and gyroscope require different calibration steps. Accelerometer has scale factors and biases which are set during factory calibration. But in every setup, a new calibration is needed for better results. Each axis in the accelerometer must read 9.81 when pointed at Earth's gravity vector. This value is used for calibration. Gyroscopes have a bias which needs to be subtracted from each reading of the sensor. To find this bias, a user-defined number of readings, which is generally above 1000, are collected when the sensor is still and then averaged. The average in all 3 directions represent the bias vector of the gyroscope. A complementary filter is used in order to process raw data coming from our IMU. Our Arduino Nano works at 250 Hz. It collects the sensor data and it does its filtering in the same loop. The complementary filter successfully eliminates the drift from the gyroscope and high-frequency noise from the accelerometer. An obstacle to eliminate is setting the initial roll and pitch angles accurately. Although the IMU is fixed on the frame, it is not completely level. When the gyro is calibrated, it is calibrated based on its current orientation, which creates a bias if the gyroscope is not completely level. To eliminate this problem, our flight controller receives its first roll and pitch angles solely from the accelerometer. This eliminates the problem since the accelerometer measures its data based on the Earth's gravitational field, which is independent from the orientation of the IMU. The total acceleration vector is calculated and divided into its x and y components. Then, using basic algebra, the roll and pitch angles are calculated using only the accelerometer and assigned as the output roll and pitch angles when the system is first started. We have decided to implement a parallel PID controller since we aim to manually tune the gain values. A parallel control is more advantageous since the P, I, and D gains are decoupled and do not influence each other, which makes the tuning process more effortless. Kp value affects the output depending on the current error, Ki accounts for all the past errors, and Kd acts on the change in error. The 3 separate outputs are calculated and fed into the motor mixing algorithm, which creates the required change in percent thrust for each motor to correct the drone towards the reference state.
We have built a testbed which consists of 2 legs to support the system, a PVC pipe and a metal rod. The metal rod passes through the PVC pipe and the pipe is free to move around the y-axis as designated in the figure. The inside of the PVC pipe was lubricated to reduce the friction, which is an unwanted disturbance in the testbed system. The PVC pipe is connected to the drone using plastic cable ties and rotates together with the pipe. When testing, the legs are fixed to the ground and held in place by using weights to ensure no slippage occurs, and the testbed only has a 1 degree of freedom, which is rotation in the y-axis. With the testbed, PID responses are easier to observe with less user error compared to trying to tune by hand. The testbed was used to obtain the P, I, and D gain values for pitch PID controller. As visible in the video, the motor mixing algorithm and the PID control system give the correct response to the attitude changes of the quadcopter. Gyro drift was another challenge we had to overcome. For this purpose, we have implemented a complementary filter. The orientation data from the accelerometer is fused with the orientation from gyro at a certain percentage to prevent gyro drift. The figures demonstrate initial random movements in y-axis before the IMU is left stationary to observe the drift. Our results indicate that the sensor fusion algorithm is successful since the angle data returned to initial value. In addition, there is no significant drift even after 15 minutes. Implementing the methods discussed previously, we were able to obtain sufficient response to fly the quadcopter. However, during a test flight, our Raspberry Pi burned, so we had to switch to an inferior controller. With this controller, it was not possible to obtain a frequency for control system to successfully correct the drone. Our goal is partly met. The drone subsystems are working correctly, but there are still some work that needs to be improved, such as increasing the controller frequency. We plan on implementing the controller system on a more powerful microcontroller with a real-time operating system. This way, processes can be completed in a designated time frame and our lag problem can be resolved.